For this part of the lesson, we're going to talk about reaction rates and chemical equilibrium. The rate of a reaction varies directly as the product of the concentrations of the reactants. Let's look at that. The rate of the reaction varies directly. It's directly dependent on the product, the multiplication of the concentrations of the reactants. For example, if we're looking at this reaction between hydrogen and iodide to make hydroiodic acid, we can have this rate expression where rate is directly proportional, okay, to the numerator here, to the product, they're multiplied, of the concentrations. I pointed out last time that those square brackets are what we use to mean concentration. It means molarity. K is going to be a constant that we're going to solve for. If we reverse this reaction, we look at the rate expression now, where rate is equal to the multiplication, the concentrations of the reactants. Okay, it's not related to the products, but the reactants in this case, which is HI, and here it's HI times HI because I have two of them. Or I could say rate is equal to the constant times HI squared. Now, in order to figure out these rate reactions, it's not always just looking at the reactants. We have to look at data in order to figure it out. So to look at a multi-step reaction, a reaction is carried out in a series of steps, and the rate of the reaction is determined by what's called the rate determining step. It's the slowest step in the whole process. An analogy that I like to use is, let's say that our class is an assembly line, and we are completing, we're putting together a toy, or a manufacturing line, and each person has a job, and their job takes 1 minute to do. So one person puts on the steering wheel, that takes 1 minute. Everyone has a 1 minute job. Somebody puts on the wheels, that's 1 minute. Somebody puts on the headlights, that's 1 minute. And we pass the cars on the minute, every minute, from person to person. But let's say that there's one person whose job is to put on the decals. And let's say that person's job takes 5 minutes to do. So what's going to happen is, as the cars get to the person who needs to put the decals on, there's going to be a backlog of cars. And so even though the whole assembly line can move along 1 minute at a time, the cars can only be produced once every 5 minutes. Now we could change that by making more people have that job, but if we look at it, that is the rate determining step. That is the slowest step in our process. And that's what I said, the rate determining step is the slowest step in the reaction mechanism. So let's take a look at this sample problem here, and I want you to follow along because it's something different from anything that we've done before. We're given a set of data, and there's 3 trials. Notice we're varying the concentration, and we're measuring the rate, how quick the reaction goes. So we have a 0.1 molar and a 0.1 molar, and my rate is 0.0076. Here, when I have a 0.1 and a 0.2 molar, my rate increases. And here, when I have a 0.2 and a 0.1, my rate also increases. So we're going to compare trials 1 and 2. And so I'm going to go ahead and put the rest of these things up here so then I can show you with my work down below what we need to do. We're going to compare trials 1 and 2. And if we look at it, the H2O2 is held constant. The HI, in this case, doubles because it goes from 0.1 to 0.2. The rate, if we look at it, the rate doubles. It goes from 0.0076 to 0.152. It doubles. So I can look at this and say, if this doubles and this doubles, I'm going to set up a little reaction that says 2 to the x equals 2. X therefore equals 1, and I refer to this as being first order in HI. And notice here's my rate done, and I can go ahead and put a little 1 here. That's indicating that I know that it's first order in HI. We're now going to look at trials 1 and 3. And I'm picking 1 and 3 because, again, I have a factor that's held constant. HI is held constant. H2O2 doubles. If I went to compare 2 and 3, notice H2O2 changes and HI changes, so they wouldn't be a good choice to use. So in this case, H2O2 doubles. HI is held constant. And if you notice my rate doubles. Again, I'm going to set up 2 to the x equals 2. And again, this is first order in H2O2. So I can go ahead and put a little 1 in there. Notice that that doesn't match my reactants. If you notice, I have H2O2 plus 2HI, but I am first order in HI because I can only determine this by looking at the data. You will have to be given data in order to do these problems. The last thing that it says to do is to calculate K. And I'm running out of room on this slide, but I can go ahead and put it up at the top. In order to calculate K, I just use my expression that I have, and I pick any one set of data, and I substitute it in. I tend to always just pick the first one. So 0.0076, and it's molarity per second, so it's moles over liters seconds, is equal to K. And I'm going to go ahead and put in 0.1 moles per liter and 0.1 moles per liter. When I solve this, I end up with K is equal to 0.76. Now, we have to figure out the units for K, and the units for K are going to vary depending on what my rate law is. I know you're not going to like to hear that. But to figure out my units, I'm going to look at this, and really I have moles over liters seconds, and it's divided by moles per liter and divided by moles per liter. So my units are going to end up being liters over mole seconds. Okay, I can show you a little shorthand of what I did up here. Moles over liters seconds, that is my one side. And then I have, I divided by, sorry, let me erase that. I divided, I'm going to move that over. I have moles over liters seconds, and I divided by moles squared over liters squared. In order to get that out of the denominator, I'm going to multiply by liters squared over moles squared, so that's crossed off. This liters crosses off, and one of those crosses off. This moles crosses off, and one of these crosses off. So I'm left with liters, moles, and seconds, just like I wrote here. Let's try one more problem. And we're going to look at NO and BR2. Here's my data. Has to be given to you. And again, I'm going to go ahead and put up my all the stuff on the side so we can see. We're going to go ahead and compare trials 1 and 2. If I look at 1 and 2, NO is held constant, BR doubles. So here I have NO, it's constant. I have, oops, oh no, I have, sorry about that, I have BR2, which doubles. And if I look at my rate doubles. Just like we did before, 2 to the x equals 2, x equals 1. I am first order in BR. That's the one I was checking out. Now I'm going to see how NO affects the reaction. So I'm going to compare trials 2 and 3. Notice again, I'm not going to compare 1 and 3 because we go from 1 to 2 and 1 to 2. So I need to hold something constant. So in this case, if I look at NO in 2 and 3, NO doubles, BR is constant, and my rate goes up by 4 times. It quadruples. I'm going to set up a different proportion this time. I'm going to set up 2 for my doubling to the x is equal to 4, because 4 quadruples. Okay? My x in this case, to the x, is equal to 2. 2 squared is equal to 4. That is where my 2 over here came from. Notice in this case it does line up with what the reaction looks like, but that doesn't necessarily have to happen as we saw in the last example. Again, we're going to solve for our constant. So rate is equal to K NO squared BR2. I'm going to go ahead and pick my first trial. 0.80 moles per liter second is equal to K times 1 mole per liter squared and 1 mole per liter. And so K is equal to 0.80. To figure out my units, again, I'll just do it up here because I'm running out of room. I have moles per liter second divided by moles cubed over liters cubed. I'm going to multiply by the inverse, liters cubed and moles cubed, which makes that go away. I lose 1 liter, and I bring that down to 2. I lose 1 mole, and I bring that down to 2. So my units that are left are liters squared over moles squared seconds. So I can put that in. Liters squared. That's not a very good squared. Liters squared over moles squared seconds. Sorry, it's not writing very well at the bottom of the screen. And so these are our rate law problems. We will practice more in class together, but at least now you have a good talking through of how to do 2 different ones of these problems. And I hope you'll come back and watch this after we try some more in class.